Welcome to the Padhai Logic Masterclass series of IoT Unit 2. Our goal today is simple, the conceptual understanding for easy scoring. Alright, so in Unit 1 we looked at the big picture of Internet of Things, and in Unit 2 we are zooming into the foundational layer where the digital world meets the reality, that is the perception layer. Think of an IoT system like a human being. A human needs eyes to see, brain to make decision, and hands to take action. So unit 2 covers the eyes and ears, that are the sensors. It covers the muscles, that are the actuators, and we'll discuss each one of them. So have a quick look at PYQ Radar. We will be discussing about what are sensors, what are actuators, what are different types of sensors, and what is the embedded system, right? And different deployment, sensor deployment strategies, what is NFC and RFID, what are the different uses of these boards in IoT, and we will be discussing about difference between embedded system, microcontroller, microprocessor. So let's get into it. Let's start with the foundational step, that is sensor. So sensor is a transducer. It is just a fancy engineering word for a device that converts one form of energy into another. Especially it takes a physical stimulus from a real world. For example, like a warmth of a room, a pressure of a footstep, or a flash of a light, and converts it into an electrical signal, or we can call it, converts it into a voltage or current that a computer can read. So it is a physical device or a transducer. What it does, it converts the physical stimulus into measurable electrical signal, right? And if you talk about the IoT layered architecture, you'll see that sensors live at a layer 1. It lives in a perception layer. So I want you to write down this phrase in your exam, that sensors are the nervous system of IoT. Why? Because without them, the cloud, the machine learning algorithms, the mobile apps are completely blind. They have no truth or raw data to process. So let's look at this creative example of the smart smoke detector. Right, so how this flows from the environment or to your phone. First, there is an input, right? So the smoke particle drift into a tiny chamber inside a sensor. Then there is the sensor, a beam of light inside the sensor that gets blocked by the smoke, right? This is known as photoelectric sensing. And after that, because the light is blocked inside the sensor circuit experiences a drop in current, translating it into digital high, or we can say if it's 0 or 1, it does convert 0 into 1 signal and sent to the microcontroller. And then there is an action taken. The microcontroller, which is the brain, it passes this data to the gateway, and the gateway pushes it to the cloud, and boom, your phone buzzes with an emergency notification while you are at work that there is smoke in your house. Now let's understand how sensors are classified. Sensors are classified based on the input, based on the output, and based on the data type. Right? When classifying the sensor by their power source, think of it as how they interact with their surroundings. That is what input comes in. So based on the input, they are divided into passive and active sensor. And if we depend on the output, it is what kind of output they are dictating, right? Are they analog sensors, means are they providing continuous smooth data, or they are digital sensors, means they are providing either binary code, either it's 0 or 1, right? And based on the data type, the sensors are divided into two parts, that is scalar sensor and vector sensor. Is it a scalar sensor? Does they give you a single number, a magnitude, right? Or they are vector, that means they give you both magnitude as well as direction. So let's discuss them in detail. So based on input, these are these type of sensors that are depending upon the external power source to operate, right? So first are the passive sensors. These are the listeners. These don't need to inject energy into the environment, right? They just sit back, absorb what's already there. Okay, so for example, a photodiode waits for ambient sunlight to hit in. A thermocouple relies entirely on external heat to generate a tiny measurable voltage. For example, a thermometer, right? So whenever you are checking your temperature, the mercury itself is increased or decreased based on what is the external temperature. So these are the listeners. They use very little power. They do not require any external supply. Then comes the active sensors. These are the radars. They don't just listen, they ask questions. They emit their own energy into the environment and measure how it changes or bounces back. Right? Think of an ultrasonic sensor on a car bumper. It shoots out a high frequency sound wave and wait for an echo to bounce off a wall and calculate the distance based on the time it took to return. So they require an external power source to generate that initial wave. Next type is based on the output, that is digital or analog. So analog sensors, these provide a continuous smooth stream of data. If the temperature goes from 25 degrees Celsius to 26 degree, an analog sensor output a smooth curve of change, right? Curve of change of the voltage. Because microcontrollers only understand binary, so you must route these signals through ADC, right? We require ADC in this. ADC is the analog to digital converter. It is required in analog sensors. Then we have digital sensors. So these are the smart sensors. They have tiny built-in ADC inside them. So ADC, the analog to digital converter, is built inside them, and microprocessing circuit directly inside their body. So instead of sending the raw voltage variation down the wire, they convert the reading internally into the binary codes like 0 or 1 and speak directly to the controller using standard protocols like I2C or SPI. Based on the data type, there is division between two, which is scalar and vector. So scalar sensors, they only measure the magnitude, they only measure the size. So they give you a single number. If you check the digital thermometer, it says 37 degrees Celsius. It does not have a direction, it's just a raw value. But if we talk about vector sensor, they give you a magnitude and a direction. So an accelerometer doesn't just tell you movement detected, it tells you that moving along the x-axis at 4 meter per second square. So it is tilting down on the y-axis and stable on the z-axis. So this is how your smartphone knows that you have rotated it from portrait to landscape mode, right? So we are focusing both on the magnitude as well as direction in vector sensors. I hope you understood the type of sensors. Let's quickly analyze the difference between analog sensor and digital sensor. I hope it must be clear till now. But the analog sensor provides continuous value, continuous current voltage, whereas digital sensors provide discrete binary codes. Either it's 0 or it's 1. Either it's on or off, right? If we talk about processing, analog sensors require external ADC, whereas digital sensors have the internal ADC integrated within them. If we talk about complexity, analog are simple hardware and complex code, whereas digital sensor has complex code, complex hardware and simple code. Basically, they are the opposite in terms of complexity. If we talk about noise, analog sensor has high noise. It is sensitive to interference, whereas digital sensors are more stable and they have low noise. Let's have a detailed discussion of what are the types of analog sensors which are used in real world, right? So very first kind of analog sensor is accelerometer. So it is it measures the rate of change of velocity Okay, if it is checking if there is any change in the position, in the weight, in anything, if there is change in any velocity, it is measured by the accelerometer. So for example, a tiny internal weight suspended on the spring used inside the industrial machinery to detect if there is any vibration or tilt. Okay, so it is attached to industrial motors, okay, to detect the microscopic or unusual vibration before the machine breaks down. Next kind of sensor we have is chemical sensor. So they identify the specific chemical substance in a gas or a liquid that is present. So it converts the chemical concentration into electrical signal and then send it further. So, for example, a carbon monoxide detector in a smart home kitchen that triggers ventilation fan whenever there is carbon monoxide detected. Alright, so it is a coated surface that changes the electrical resistance when the targeted gas modules stick to it. Okay, so whenever there is carbon monoxide stick to the detector, it changes the electrical resistance and start performing the action, that is starting the ventilation fans. Next we have humidity sensor. So these are the type of sensor which are used to measure the moisture content in the atmosphere. Alright, so they use captivating sensing where the moisture changes the electrical capacity into the sensor material. So there is a material that act like a sponge inside the detector and it observes the airborne moisture. Its capacity to hold an electric charge shifts. For example, smart farming probes buried in soil, right? Smart sensor, they are buried in soil to trigger the water sprinklers whenever the ground dries out. So they are reading, constantly observing what is the capacity of moisture inside the air, and once they get to know that, they sprinkle the water. Then we have level sensors. So level sensors are used to detect the level of liquid or powders in a container. So it is a continuous vertical strip or a float system inside the container. This sensor is a continuous vertical strip. So whenever, for example, there is a liquid food manufacturing tanks, okay, so that output, that when it is completely empty it gives us 0, and when it is completely full please gives us 5. So this is done by using the level sensor, which is put inside the container to check what is the level of the food or liquid food which is inside the container. Next we have is the PIR or motion sensor. So these are passive infrared sensors, detect heat energy emitted by living beings. So whenever there is a warm body which passes through the sensor, it creates a voltage pulse. So it is a lens that splits the vision into zones, tracking moving pockets of body heat. So whenever there is a moving living being, it is always warm. So it identifies that. For example, the smart office hallways where light instantly switch off if no human body heat signatures move for 5 minutes. And then whenever there is a movement, the light switch on. That is how motion sensors work. Then comes the optical sensors. These are also known as light sensors. They are responsible for resistance, provide the light intensity, increase or decrease according to the voltage change. For example, city street lights that autonomously dim down or brighten up based on the changing cloud cover and sunset times. Okay, so an LDR, light dependent resistor, is present in this, whose resistance drops when it hit by photons. Okay, and next we have pressure sensor. Pressure sensor is a tiny flexible diaphragm type of equipment that is equipped with a strange gauge that bends under the physical force. For example, smart water grid that detect a sudden drop of pipe pressure, indicating a water main burst down the street, for example. Okay, so the pressure sensor, there's a diaphragm like you see in a human body. So it deforms under the force, and whenever it does, it produces a voltage. It produces a voltage output to perform the particular task. Then we have proximity sensors. So they are used to detect the presence of nearby objects without physical contact. So it is used, what it does is it emits a shooting invisible beam. Okay, there's an invisible beam that is shooted from the sensor, and the closer an object gets, the stronger the reflected beam bounces back. For example, car parking assistance system. All right, so when you're reverse parking, right, so there's a beep that is faster as your bumper approaches the wall, right? So that is the proximity sensor working. Then we have temperature sensor. So it is the most common type of sensor, and what it does, it is its resistance changes predictably as the temperature rises or falls, right? So there is an internal electrical resistance that is changing according to the ambient heat. For example, preventing a gaming laptop CPU from melting by tracking its thermal output in real time. So that is where we use temperature sensor to make sure that things do not wear out because of the rising temperature. Then there are touch sensor as well, where we are capturing touch, measure the change in the electrical charge when a human finger or something gets near the sensor. So it has a panel. The panel detects the electrical capacity of human skin when a finger draws close. So it is very for example, there is a sleek waterproof control panels on high-end smart washing machine. So whenever the human finger touches that sensor, it automates and start doing the work it is designed for. Now let's talk about digital sensors. If analog sensors are like traditional thermometers where you can look closely at a line of mercury to guess the value, digital sensors are like your digital dashboard or Apple Watch. They don't just feel the environment, they process it right on the spot. So inside the digital sensor, you would see there is already an ADC, which is analog to digital converter, which is converting the crisp 0 and 1 using an internal ADC. And because they speak this smooth binary language, that is 0 or 1, they don't send the varying voltage down the wire. Instead, they transmit the actual data packets directly to the IoT gateway or microcontroller using standard digital communication like I2C, which is the inter-integrated circuit, or SPI, which is serial peripheral interface, or UART, which is universal asynchronous receiver transmitter. It's like sending a precise text message instead of just sending fluctuating radio signals. So what are the different types of digital sensors? First, we'll talk about digital accelerometer. So imagine you have an analog accelerometer on a vibrating machine. It outputs a voltage, say 1.2 voltage from the x-axis and 2.4 from the y-axis. Alright. And if the wire connecting it to your microcontroller run past a heavy power cable, electrical interference or noise will corrupt the voltage. So your 1.2 signal might arrive as 1.4. So there is completely the data accuracy is completely ruined. That is why we have digital accelerometer. So they changes the game. What happens? It computes the precise g-force value for the x, y and z internally. Then it packages those numbers into a clean binary string. Okay, for example 0 1 1 1 0 0 1, and ships them out. So all the electromagnetic noise cannot easily turn this distinct high voltage into low voltage problems, right? So making the digital sensors or digital accelerometer sensor very reliable and immune to electrical interference. All right, and the second we have is digital temperature sensor. So you see, this is a little component showcase, one of the coolest architectural advantage of digital system. So if you are using analog thermistors to monitor the temperature of 5 different rooms in a building, you would need 5 separate analog input pins in your microcontroller. So your wiring would look like a bird's nest because there will be a lot of wires. But if you talk about digital temperature sensor, it has various names or various IDs encoded for everyone. So because they have unique name, you can chain dozen of these sensor into an exact same physical data wire. You don't need multiple wires, and the microcontroller simply calls out that, hey, sensor room 3, what's your temperature? And only that specific sensor respond back to the binary payload. Alright, I hope you understood how digital temperature sensor works. Now let's pivot our understanding from input to output, right? So let's talk about actuators. If you build an IoT system that only has sensors, you haven't built an ecosystem. You have just built an observation port. You can watch the world burn, but you cannot pull out the fire. Actuators are the component that pull out the fire. They are the component that turn data into action. They are responsible for moving and controlling the system. Alright, they convert this data into physical motion. So why are they vital? So in IoT system, actuator receives the command from the microcontroller and execute the physical action that is required. Alright, so they are essential because they perform automation. They physically move their belts or open water valves without a human turning a wrench, right? So they are doing things automatically without human invention. And there is in safety. If a chemical sensor detects a toxic gas leak, a solenoid actuator can instantly drop a shutter to isolate the room. So it ensures that there is safety, that it provides the safer environment to work on, right? Without a human constantly detecting if there is a gas leak or not. It also provides remote control. They allow you to open your house windows or unlock a door for a delivery driver from thousands of miles away via a smartphone app, right? And it also provides the precision control, like moving robotic arms with sub-millimeter accuracy as well. Alright, next we'll talk about what are the types of actuators. So there are various types of actuators which are used in IoT. So let's talk about the massive 4 types of actuators, right? So first is the electrical actuators. These are the absolute favorite of IoT world because they run on electricity, which our microcontrollers have plenty of. Alright, so they convert electric energy into mechanical torque, or we can say into linear motion. For example, DC motors. So these are the type of electric actuator which spins continuously and rapidly. Think of a smart cooling fan or an automated vacuum cleaner. Then we have servo motors. They don't just spin continuously, instead they rotate at a highly precise angle. For example, exactly 90 degree based on the control signal. You see these steering wings of drones or moving robotic finger joints. So they are the servo motors working. Then we have solenoids. These are the basic electromagnetics that push or pull a central plunger into a straight line. So when you tap your key card to a hotel door room, that sharp click you hear is a solenoid snapping back and pull the lock bolt open. Then we have stepper motors. These rotate in tiny ultra precise angular increments or steps. So if you ever watched 3D printer head moving smoothly back and forth to lay down plastic, you were watching the steeper motors at work. Next kind of actuators are hydraulic actuators. So they rely on pressurized liquid, typically on oil. So these are the heavy lifters of industrial world. They require massive pumps, fluid reservoirs and thick hoses, meaning that they are prone to leak and high maintenance. However, they deliver immense mechanical force. So you will find these controlling heavy buckets of IoT enabled excavators or vehicle braking system. Then we have pneumatic actuators, right? So instead of oil, they use compressed air. They are incredibly fast, high responsive and structurally clean, because if there is leak, it's just air escaping into the room. There is no hazardous oil leak. And they also possess a natural mechanical springiness. You'll see that these are everywhere on high speed industrial assembly lines, running pneumatic grippers that rapidly pack products into boxes. And then we have thermal or magnetic actuators. So these leverage the cutting edge material science. They utilize sharp memory alloys, okay, that is known as SMA, that physically contact or expand when exposed to specific temperature. Because they don't rely on gears or motors, they can be made incredibly small, making them perfect for micro medical devices, like you see automated insulin delivery pumps inside the human body. That is where they are used. Then we also have mechanical actuators. So these don't just transform the type of energy, they simply transform the style of movement. A classic example is a rack and a pinion system. It takes the spinning rotary motion of an electrical motor and converts it into a linear motion to slide heavy automated driveway gate. That is where mechanical actuators plays a vital role. Let's bring our all discussion together with this critical comparison matrix, that is difference between a sensor and the actuator. So primary role of sensor is to monitor and perceive the environment, whereas the actuator not only perceive, it execute the physical action based on the what sensor has perceived. If we talk about function, sensor converts physical energy into electrical signals and actuator converts these electrical signals into physical motion. And then there is a direction of flow from the environment to the system, but actuator is from the system to the environment. And if we talk about system analogy, sensors are like eyes and ears, and whereas actuators are the muscles that acts like arms and fingers and do that particular thing. For example, your finger touched a hot pot. The way it touched, the sensor activate inside your body, the message reach to the brain that it is hot, and your fingers are immediately pulled back. So that fingers immediately pulled back is done by the muscles. These are the actuators. And the touch, which was sensing the hot, was the touch sensor inside your body, right? I'm giving you an analogy of discussion, right? Next we have placement. So sensors are mostly located at the input port of the system, whereas actuator is located at the output port. There is a physical stimulus, and then it goes to electrical signal. There is electrical signal, then it goes to physical work. So there is environment sends the physical energy to electrical signal. These electrical signals are sent to the microcontroller, which is the brain, and then these are sent to the actuators, and actuator does the actual work in the physical environment. This is how it actually works in real life. Now we are breaking down a technology you use almost every single day without realizing it. It is RFID. which stands for radio frequency identification, and we'll also talk about its close cousin, which is near field communication. So back to the traditional barcodes or QR codes on a pack of chips. So to scan them, you need a direct line of sight. The laser beam must be physically point at the printed pattern. Otherwise, it won't able to identify it, right? But the RFID technology completely smashes this limitation. So it is a wireless technique of identifying the objects, tracking the objects using radio waves, right? So we are using radio wave transmission to identify, track and capture the data from object automatically, even if they are buried inside a shipping box, even if they are inside your leather wallet, it doesn't matter, right? So in IoT architecture, this is a vital pillar for AIDC. AIDC stands for automatic identification and data capture. So RFID technology is the vital pillar for this, and it enables physical item to broadcast their identity directly to our digital networks without being physically pointing at the pattern. So if we talk about how the core magic works in an RFID tag, there are two major basic primary components of RFID. First is the RFID tag, which is attached to the object, and then we have an RFID reader, that is the antenna, which is the scanning device. So the core magic relies on the internal antenna transducer that convert electrical current into radio waves. And when the reader generates the electromagnetic field, the tag intercepts it. Alright, and depending upon the frequency, the physics of how they talk completely changes. So this is discussed in the different types of RFID. First we have ultra high frequency RFID. So this is a speed demon. It operates via the phenomena called backscatter. So what happens is the reader blasts out a powerful radio wave, and the passive tag observes a tiny drop of energy just to boost up its internal chip, and then it reflects. Alright, then it changes the signal from the what the reader has sent, and from that the reader is able to encode the data which is sent to the reader. And this works for several meters, allowing a data warehouse scanner to log an entire shipping pallet of goods in just a fraction of a second. Then we have high frequency RFID. So this is what you carry in your pocket. It is found in passports, in modern credit cards, and unlike ultra high frequency, it does not use backscatter. Alright, it relies on NFC, near field communication. Alright, so the reader and the tag must act like a split transformer over a short distance, like a few centimeters. So NFC is simply a specialized sub branch that restricts communication to an ultra close range, usually under 4 cm, offering highly secure point-to-point data exchange for contactless mobile payments. Alright, and then we also have low frequency RFID. So it is the oldest type of technology, and it has very short read range and very slow data speed, but its radio wave can pass effortlessly through liquids and animal tissue as well. So this is exactly why it is universally used for livestock tracking and microchipping pets. Now, how does an RFID system actually execute this data capture? Let's break down the physical working principles step by step. So very first is the energy conversion. It all starts with RFID reader. The reader contains the electro circuit connected to the radio antenna. Okay. And this transducer takes pure electrical energy from the power supply and convert it into an invisible electromagnetic wave. And then there is an object carrying the RFID tag enters the invisible radio field, and if it is a passive tag, meaning it has no battery, then the tag's own tiny internal coil antenna intercept those radio waves. Through this process called magnetic induction, the radio wave magically generate a tiny electrical current inside the tag. And then once the tag wake up, right, once the tag wake up from this burst of wireless power, it can do two things: read mode or write mode. The tag internal microchip broadcasts its stored data back through its antenna, which the reader intercepts and decode. Or what it can do, write mode. The reader can actually broadcast the heavy data signal to change the information inside the tag's memory, like changing an item status from in warehouse to shipped. Alright, so if we talk about the architecture to make this commercially viable, what engineers do is they manage a brilliant feat of manufacturing. So they took CPU, they took memory, storage, a radio transmitter and a receiver, and shrunk them into down in so tightly that they can be combined into a single microscopic silicon embedded chip sticker. This is why you can find an RFID tag stuck into a simple $10 shirt in a retail store, because it's cheap, it's flat, and it's incredibly powerful. We must know what are the benefits and vulnerabilities of RFID. So if we talk about advantages, it has no line of sight required, means you can read a tag hidden inside a suitcase as well, right? And then there is bulk mass reading. A reader can capture unique IDs and hundreds of tags simultaneously in just seconds, right? And then you see we have high storage and real-time access. So unlike static barcode, you can write new data into the RFID chip dynamically as well as it moves through a factory line. So it is a biggest advantage. We also have few vulnerabilities like security and eavesdropping, right? So radio waves can travel through air. If not strongly encrypted, anyone with a hidden high powered reader can intercept your card data from short distance away. So this is very crucial thing. And there is also a foil shield effect. Because it relies on electromagnetic fields, you can completely blind a standard RFID tag by wrapping it into 2 or 3 basic layers of household aluminium foil. So it acts as a Faraday cage blocking the radio signals. Alright, and then we have cost as well. So active tags that rely on internal batteries are expensive to manufacture and maintain over the time. I hope you understood the concept of RFID. If we talk about real world application, it is used in multiple things. It is used to monitor what are the whereabouts of vehicle, train, containers. It is used to keep tabs on valuables, where they are right now. Also, it is a credit card size access that is used for many purposes. It is put to use in HR system as well, limiting who may enter secure locations. It is also used in ID badge, alright, and logistic planning and execution, where RFID plays a very vital role. And it also helps in elimination of fake goods. Like you see in pharmaceutical industries, fake drugs are a massive global hazard. So high-end pharmaceutical companies print a tiny RFID tag directly into the pill bottles. So as the box travels from the factory to the pharmacy shelf, scanners verify its unique cryptographic ID, ensuring that no fake lookalikes were swapped in the way. Let's shift our focus from identifying single items to monitor massive physical environment. Welcome to Wireless Sensor Network. So, and WSN is an infrastructure free, self-organizing collective of thousands of tiny autonomous computing devices called sensor nodes. Alright, so what happens in this is, instead of routing heavy cables through the forest or factory floor, there are nodes that communicate with each other wirelessly. Alright, and they gather the raw ecological matrices like heat, sound, pressure, and hop the data from node to node across the network until it reaches a one point called sink or a base. Alright, so sink act as a bridge, that is allowing human operators to inject queries and pull out real-time analysis. So you see over here, there is a field of sensors, and all these sensors are hopping their data and until they reach a base station or a sink, and through this sink the data is sent to the server for the analysis. So what makes WSN unique compared to the standard Wi-Fi network is its design constraint. Alright, so it is used as a server power constraint. Nodes are frequently dropped into harsh environment where changing a battery is impossible. That is why we require WSN. It also provides resilience and tolerance. If a wild animal destroys a sensor, right, what happens? The network shouldn't crash. The remaining nodes must dynamically find a new path to route the data around that dead node. And then it is also required to scale, to provide scalability. For example, your network needs to expand from 10 nodes to 10,000 nodes. So it should be done seamlessly without rewriting the entire architecture. So that is why WSN is very important and it is unique from Wi-Fi network. So there are different types of WSN. If we talk about types, first is terrestrial. So it is the most common type. It is deployed on open land. Alright, it is deployed on land, like across cities or forest. So they can be dropped randomly from a helicopter, for example, or placed precisely by the engineer. It depends on whatever the requirements are, and they use ultra low power protocol to conserve their limited batteries while monitoring the environmental trends. Then we have underground WSN. So here the nodes are buried deep inside the soil or agriculture field or mining shafts. So the challenge is that the high frequency radio wave travel terribly through the thick mud, rock and underground. So the signal suffers the attenuation, means the loss of strength. For example, precision agriculture field utilize the buried underground node to map the soil moisture and communicating with heavy duty signal boosters to optimize the robotic irrigation. That irrigation wall should open. Then we have underground water WSN. So they are deployed beneath the ocean, inside the water reservoirs. So what happens is the radio waves are virtually useless underwater. Therefore, underwater WSN swap radio waves with acoustic transceivers. Okay, so we are not using radio waves over here. So what the catch is that sound travels much slower than light, leading to high latency, but it is vital for oceanic pollution or tracking underwater oil pipeline. So that is why we are using sound waves instead of radio waves, because radio waves are not efficient in underwater. Alright, and then we have multimedia WSNs. So these are the traditional WSN which handle tiny text-based number like sending 24 degrees Celsius once an hour. So multimedia SN are equipped with digital cameras and microphone to process rich stream of videos, audios and images. And they require heavy bandwidth and robust processor, making them perfect for advanced facial recognition security parameter, right? And lastly, we have mobile WSN. So these sensors aren't static. Okay, they have wheels. So basically we are talking about our own phone. Okay, so they can physically move and adapt to the changing situations. For example, during a hazardous chemical warehouse fire, human firefighters cannot enter safely. Instead, what we do, we send an autonomous mobile drone sensor which can fly inside the smoke, map the spreading toxic fumes, and dynamically shift their position to maintain a strong communication link between the command center. That is how mobile WSNs are used. So there are various applications of WSN. First is environmental application, which include forest and animal identification. If there is any flood, if there is any kind of activity which needs to be monitored, so it is widely used for that. It has a wide use in military as well, to track and environment monitoring, surveillance, and the sensor network are deployed in multiple areas where it is a very high area for security threats. And if we want to keep the tap on the enemies, if there is any particular movement which needs to be monitored, then WSN is also used in healthcare application like patient and doctor tracking and monitoring. Also, it is used in traffic monitoring to understand where there is traffic, to dynamically route the management, parking lot monitoring, and so on. And other purposes as well, industrial process monitoring, building temperature management, and also civil structure health monitoring are also vital applications of WSN. Let's look at a fascinating shift in how we collect IoT data. If we talk about traditional wireless sensor networks, it rely on deploying dedicated, expensive static hardware sensors on the stations, right? But if we talk about participatory sensing, it is completely flipping the model on its head. So instead of installing thousands of new physical sensors, it leverages the existing hardwares of billions of people already carrying around in their pocket. That is the smartphones or the tablets and the wearable devices. So every day citizens become mobile sensors. So we use the public daily movement to collect and share the data over vast geographical areas to analyze the real world processes. So think about it. What is packed inside your phone right now? You don't just have a device to scroll social media. You carry a powerhouse of sensor, a high resolution camera, a sensitive microphone, a highly accurate GPS tracking, an accelerometer, etc. So participatory sensing simply crowdsources this data, right? So it is using where individuals communicate and use their personal mobile devices. So it use dedicated static infrastructure and turns it into everyday citizen into mobile sensor, right? And what it is doing, it is leveraging the existing sensor rich hardware which I told you about our phones, and gathering the information that is geographic wide. So there is no geographical boundaries of carrying the collecting this data, right? If we talk about key characteristics, first is human in the loop. So this is a vital technical distinction. There are two ways a phone can gather data. One is opportunist, where your phone silently collects the data in the background without you knowing, right? And participatory sensing, however, actively involves the human. The user must make a conscious decision to participate, like actively clicking a button to report a pothole, tapping an app to verify a location, or opening their camera to log pollution. Then another is the vast scale. Imagine trying to map traffic across the entire country like India using fixed road sensor. It would cost billions. But with this sensing technology, you scale instantly across citizens and state because you are riding on natural organic movement of human population. And then there is cost effectiveness. The organization or the tasker running the project doesn't spend a single rupee on buying the hardware or maintaining battery life, because the user already owns, charges and maintain their infrastructure, that is their phone, and which is entirely for their own personal use as well. So it is quite cost effective. So if you see at this, there is a server and there is participants. These are continuously sensing the task, and through the participant the server is sensing the required data, and this is done globally to understand the what is actually working. Now let's quickly look at this two brilliant real world example that perfectly illustrate this concept. So first is the Waze or Google Map crowdsourcing. When you are driving and encounter an unexpected traffic jam, an accident or a speed trap, you actively tap your screen to report it. That single manual action updates the central cloud server and instantly altering the navigation route for thousands of other drivers behind you. This is the participatory sensing in action. Then there is a noise tube project. So this is a worldwide citizen science research initiative. What happens is that citizens download an app that safely accesses their phone microphone while they walk through their neighborhoods. By actively logging local noise levels, everyday citizens collectively generate high resolution block by block noise pollution maps of major cities, showing the urban planner exactly how these acoustic barriers are needed. Now we'll discuss about the embedded system architecture. So if you look at a standard laptop or a desktop computer, it is a general purpose computer. It is designed to do thousands of different things. You can write an essay, play a high-end video, or compile a code. But an embedded system is completely different. It is highly optimized structural architecture, which is the combination of hardware components and software components designed to do one dedicated real-time function. And it is subject to strict power, cost, and physical size constraint. So think of an electronic controller inside a washing machine. It is highly optimized to perform one dedicated specific task only. For example, a smart microwave or a pacemaker, right? So let's look at the architectural stack. First is the peripheral hardware, or it can also known as the actual physical layer, the perception layer, right? So it is the peripheral hardware. It represents the perception layer of IoT devices, right? So it contains the three interconnected elements, that is sensors, actuators and drivers. So drivers, think of driver as a muscle power plant. An actuator might know how to move, but the drive circuit provides the heavy physical voltage and current that is required to physically spin that heavy torture in industrial motor or to push a hydraulic rod, right? So what is the muscular power plant which helps the actuator perform the task are the drivers, right? So these are the three components of first layer. Then we have the layer 2, that is embedded system. It is the brain. Directly above the peripheral is the heart of the machine, embedded system. This is microcontroller or the microprocessor that handles the thinking, data cleaning, decision making, everything. And it relies on three critical components. First is connectivity protocol, right? So connectivity protocol are the languages, system languages which is used to talk to the external world. So depending on the range and power limit, it selects whichever is required. For example, for a short range you might opt for Bluetooth or Zigbee, or for long range option you might opt for Wi-Fi or Ethernet, right? Then we have IPv6 address. So in an IoT network, every single device must have a unique identity so it can be reached over the web. So old IPv4 standard only allows roughly 4.3 billion addresses. Okay, so it only allowed 4.3 billion addresses, which were not enough. So because we were connecting 10 billions of smart devices, the embedded architecture specified IPv6 address, which uses 128-bit addresses, offering an virtually infinite number of unique IP addresses. And then we have connection services. So these are lightweight software layer responsible for packaging and shipping data efficiently. So what happens, instead of using heavy web protocols, right, we use protocols like MQTT and COAP to send the data packet using very minimal battery power, right? And then comes the layer 3, that is local network. So first, what happens, let's trace how the data travels away from our devices into our wider world. First is passes through the local network. So the device might connect to the traditional LAN inside the home or a WAN, that is wide area network. However, in advanced industrial or military IoT setup, devices often form a MANnet. MANnet stands for Mobile Ad Hoc Network. So it is a decentralized router-free network where individual smart devices connect directly to one another. So if one device moves or fails, the remaining devices automatically reconfigure their network path on the fly. Alright, and from the local network, the data hits the global network. So it reaches the cloud infrastructure, right? And where the massive server store where we process and run machine learning algorithms on a collective data. And the journey ends at the other devices. This represents the ultimate destination of the information, right? It is the ultimate destination, whether it triggers an automated machine-to-machine command to shut down the industrial pipeline, or it sends a real-time status update to the user smartphone interface miles away. It depends on the needed action. Now let's have a quick look on how the IoT prototyping boards work. So if you want to build an IoT device, you can't just plug a sensor into thin air. You need development boards to read the sensor data, execute your code logic, and transmit the result. Right. So let's talk about the very first kind of board, which is Arduino. So it is an open source hardware and software platform which is used for prototyping the IoT devices. So it is a simple, highly accessible design which is running for 8-bit or 32-bit AVR or ARM controller chip. Okay, because it runs on bare metal, meaning it has no operating system. Alright, it has no operating system, and what you do, you write a code on a beginner friendly Arduino IDE using C or C++ language. Alright, and if you want to give basic Arduino board cellular data, you use Wi-Fi. Alright, and there are multiple variety of input output pins on the board, interfacing with sensors, actuators, and other peripherals. So you can have a look on how Arduino board looks like. I think you can see how it is, and there are various kind of elements which are part of this Arduino board. There are various kind of pins. Alright, next let's move on to the second type of board, that is Raspberry Pi. So unlike Arduino, the Raspberry Pi is a complete desktop grade single board computer. Alright, so there are two types of board. First is the microcontroller, okay, which is Arduino. Second is single board computer. So what is the difference? You see, a microcontroller is simple bare metal chip, and it is designed to repeatedly run single specific loop of code. Whereas the single board computer, for example Raspberry Pi, is used, and it has multiple elements. It is fully functional. It is a miniature computer. So it contains RAM, storage, video output, and a complete operating system like Linux. Alright, so Raspberry Pi is the single board computer. I hope you understood the difference. And it features a high performance, okay, and it has gigabytes of RAM and USB ports for mouse and keyboard, and it also has HDMI outputs to drive external video monitors as well. And it also support multiple languages for IoT development, and the actual operating system on it is Linux based operating system. So there is Raspberry Pi OS. Alright, so this means that it can multitask. It can run on complex Python script, and it can also host a database, process real-time video feeds as well. So it is a multitasking board. Next we have BeagleBone. This is also SBC platform. Alright, so beyond Arduino and Pi, we have BeagleBone and Intel as well. So if we talk about BeagleBone, it is a powerful Linux based SBC only. However, it is optimized for industrial process. Seriously optimized for industrial and robotics. Why? Because its board layout features a massive arrangement of expansive header pins. So it gives engineers access to specialized real-time coprocessors, allowing it to control highly complex industrial machinery. And then we have Intel Galileo, which is it was Intel's entry into IoT prototyping market, and it bridged the gap between worlds. It features a low power Intel Quark processor running a lightweight, okay, Linux distribution, yet it is explicitly Arduino certified. So it is a kind of hybrid. So this means that it has exact physical pin layout of Arduino, allowing engineers to plug standard Arduino sheet directly into the Intel architecture. So it is primarily utilized by developers that are aligning their IoT system with enterprise level Intel network. So this, guys, brings us to the conclusion of Unit 2, the core elements of the perception layer. So let's quickly recap the entire unit framework to ensure that you perfectly score in your upcoming assessment. So pause this video, try this PYQ radar, and I hope now you are able to understand what are the sensors, difference between different types of sensors. We looked at actuators. We shifted to external crowd paradigms like participatory sensing, WSN, RFID, and we also examined the embedded system architecture as well. So please keep it up, keep your concepts clear, keep practicing, and I'll see you in Unit 3.